Welcome back everyone to the NPTEL course on topological phases of matter. We are studying model Hamiltonians for topological semimetals and topological insulators. So, we have studied toy models, SSH model and Rice-Miller model. Then we looked into more material specific mechanism for getting Dirac cone through graphene lattice, Rasmussen spin orbit coupling and tight bending hopping between even and odd orbitals. So, we have now all the ingredients. Now, we have to gap out those Dirac cone to get topological insulators. And here again we will talk about few popular materials before we become more creative about studying different types of topological invariants based on the inputs that we learn here. Okay. So, we start with graphene and we have to gap it out. So, we have to give a D3 term that changes sign through synthetic gauge fields or magnetic field, and that is called Haldane model. Okay. So, graphene with spin orbit coupling was done by Kane-Milley, Charles Kane and Eugene Milley, called Kane-Milley model, where 2 sublattice plus 2 spin gave us a 4×4 Hamiltonian. So, we could get 2 Chern insulators by a combination of different spin and orbital with opposite Chern number. These are called quantum spin Hall insulator. There is a slightly nuance here that whether you can really split these two Chern bands separately or not, we will discuss that. But if you really cannot differentiate those two bands with opposite Chern number, which turns out to be degenerate, we will redefine a new topological invariant called Z2 invariant in the time reversal invariant case. And whereas here you can get a quantum Hall effect or Chern insulator without real magnetic field was the main point of this work. So, then with Rasmussen spin orbit coupling, let me do it. Starting from Rasmussen spin orbit coupling with again 2 quantum wells, of mercury telluride and cadmium telluride. One can again engineer, one can gap out the degenerate band and get 2 copies of our quantum spin Hall insulator, and this was the famous Barnevik gas Jang paper. I will give the reference later. And with opposite RASPA spin orbit coupling, bilayer, we can also get quantum spin Hall insulator. This was done by us. We will also give you the reference later. And one can do the same thing with the other tight binding hopping, and also one can mix those between different layers with even an odd orbital and getting also a linear term along the z direction, whereas you already have a linear term along x and y directions, and we can get all sorts of Dirac cone, 3D Dirac cone, topological insulator, and so on. So these are the main 3 ingredients, but not necessarily one has to be restricted. We will mainly focus on Haldane model here, and for the other ones which are the quantum spin Hall insulator, we need some help of symmetry. So we will do that after we take a detour to talk about symmetry, and we will come back to other models. But Haldane model does not require symmetry. It actually breaks a time reversal symmetry because we are going to add a synthetic gauge field. So, but the essential physics is what we have already discussed, so you can understand without knowing the symmetry. Okay, so Haldane model started with the honeycomb lattice, and it was done even before the graphene was discovered. The graphene was discovered in 2006. So this was more of a honeycomb lattice tight binding model that he started with, and the tight binding model was also there much earlier by Wallace in 1960s, where also he showed that there will be Dirac cone. So in the K space we found the Dirac cones were along these points, right, along these high symmetry points, and those 2 Dirac cones had opposite chirality. Now that reminds us of what we have studied in Rice-Millet model. We had 2 Dirac cones at gamma point and at m point in a square lattice, and we needed a D3 term that will change sign between them. So here also we need to engineer a D3 term that will change sign between K and K prime point. So I need a D3 term, let us say it will be plus here, plus here, plus here, and minus everywhere. Equal to 0 contour. So it does not matter where it is, but as long as it encircles K prime or K, right, it can be equally done with this K. So how do you get it? So it turns out it is not that easy. These are my sublattice. Let's call it A. So D3 lies at the diagonal term. So which has to be then the hopping from A to A and B to B. So or let's show this for B, and it will be the same, some T prime, T prime, T prime, and if you do the same thing along A also, there will be A to A, and by symmetry it will have all the same hopping, and the second nearest neighbor terms are plus A1 A2 So there are 6 of them. So let's just denote them as second nearest neighbor. So if I do that, and I will get term like, it will be minus T prime M e to the power I k dot delta prime M, and a BB also same term. And if I have a Hamiltonian, these terms we already worked out. Now we are working out this. We can see that because it is the same atom, carbon atom is sitting, so the hopping is same. So there is no difference between these two. So there is no D3 term. So what Haldane proposed is that let us put some on-site potential difference between them. That will give us a D3 term, which will be then M, just M, because that is the only difference between these two, and that is K independent. How to obtain it and all, with putting some different potential, on-site potential to different carbon atom maybe. It has to break the sublattice symmetry. Now the two sublattices are different, and nowadays we can engineer such things, and at that time it was more of a toy model thing. But even if you put that, you will get a constant M, constant D3, and we say that constant D3 will give an insulator. That is what happens in bilayer AB stacking graphene, that A and B has a different on-site potential, so it will open a gap, but that will be a trivial gap because D3 is fixed sign everywhere. But we need a D3 that will change sign in the Brillouin zone. So what he also proposed that let us put a chiral phase we use a different color. associated with the hopping, with all of them. And chiral phase is what? We already talked about that. Chiral phase is when you have some sort of a gauge field or magnetic field or vector potential. Again, the origin was not specified. Later on, when cold atom people in which they can engineer synthetic gauge field, they realized Haldane model experimentally, but for us it is kind of a synthetic gauge field or potential that is put. And now you also need, if you put the same potential, you will get some term, but that will again vanish from both sides. So you have to put it to be different. And the Haldane proposal was hopping A to A, it is again the T prime, but put opposite chiral phase. Okay. All right. So now we will have a D3 term, and that will be or let me write the explicit expression for will be 2 T prime M cosine k dot delta m plus phi plus m, whereas BB would be minus phi minus m. So that D3 will be, which is the difference between the two on-site term, this will be 2 T prime sin phi plus m, and there will be a trace term or constant term that we can work it out. The Hamiltonian then would be plus D3 sigma 3, we already have D1 sigma 1 and D2 sigma 2 from the hopping between different sublattices, which gave us Dirac cone. But now we get a D3 term. This term does not make much of a difference, just a shift of the band structure. Now this is our interest. We still have to have our parameter space, and these are the two parameters we have, T prime and M, such that this will change sign within the Brillouin zone. Right? If 0 gives us the condition that sin phi has to be less than m by 2 T prime So rather there are two parameters which are, T prime is set by the band structure. So in real materials we do not have a choice to tune it, but this is the external gauge potential and this is the external on-site potential. So these are the two tuning parameters. here nothing can be tuned. So, the gauge potential sign of that must be less than m. That is our criteria. So, this one we can evaluate, we can do little more and we can evaluate this term. We already know what are delta m prime terms given, and we can work it out this. So, this will be homework to put all those terms and show the value of at k equal to k and k prime k dot delta m prime just gives you plus minus 3 root 3 by 2. So, that dispersion term at this 2 point changes sign, plus 3 by 2 and minus 3. So, it is good news that this does change sign between the k and k prime point, but this also change sign. So, we still have to play with this two. So, d3 around k is equal to m plus 3 root 3 t prime sin phi, and d3 at k prime equal to m minus 3 root 3 t prime sin phi. So, you have to choose m and phi such that m is not always greater than this. If this is always greater than this, then you will have, this will always be positive, this is also positive. So, the criteria then is m is to be less than okay, and let me sin theta can change sign. So, m should be less than equal to right, or even I think this is okay. So, you can draw a phase diagram, and of course, the Chern number we have already worked out will come from k and k prime. These are the 2 points where the Berry curvature, Berry connection was diverging, right. So, it only comes from those 2 points, and we have worked it out for Rice and Millet model that everything else cancels out except the, it only depends on the sign of d3 at k minus sign of d3 at k prime. So, with that we will have this phase diagram as a function of phi and m. So, at phi equal to 0, m can be 0. So, when phi equal to pi by 2 and minus pi by 2, this is where sign is 1, and then it says that m has to be less than this. So, it has to be, if I write it as, so these are the two boundaries, which is T prime and 3 root 3 T prime minus, and at phi again m goes to 0. So this gives us in this case Chern number is +1, in this case Chern number is -1. Okay. Whereas outside Chern number is 0. So these are the trivial one, these are the Chern insulator. So Chern insulator with opposites. So these are the Dirac points. When m equal to 0 and theta equal to 0, d3 equal to 0. So and at pi also. So you go from, so this is much like the Rice-Miller phase diagram, except that there is a phase boundary which are kind of a sinusoidal because of the choice of the gauge field. Okay. So this gives us the first hope rather, or a model to get a quantum Hall effect or quantum Hall insulator without really a magnetic flip from outside. And it was done in 1989, and then it took much longer time for other people also to propose a similar thing of quantum Hall effect without magnetic field. But there the synthetic gauge field is something that one could not generate earlier, but a similar term of synthetic gauge field, or that term can be obtained from spin orbit coupling, and this is where Haldane model became famous, and so on the field started developing. So next class we will go to talk about topological superconductor before we come back to symmetry and topological insulator with spin orbit coupling. All right. Thank you very much for your attention.